Welcome to Planetary Exploration. I'm sure many of you watching this video right now have asked themselves at some point questions like, is there life on other planets? Is the universe finite or infinite? Or will humans ever live on Mars or other planets? While some of these questions probably cannot be answered at all, some definitely can be answered by exploring the universe. And well, exploring the universe is a giant task. But you have to start somewhere, and one of these starting points is our solar system, nearby planets and planet-like bodies, moons, asteroids, and the like. But as you may know, other planets, or rather their environments, are a lot more hostile than that of Earth. Not to mention that sometimes spacecrafts fail to get to their destination altogether. Add to that the fact that sending a robot to space is a lot cheaper than sending a human, and the point I'm trying to make is becoming quite obvious. Exploring planets is primarily done via robots, or if we use the proper term, robotic spacecrafts. And that is not to say that once we start sending humans again, robots won't be needed anymore. Robots will still be needed to perform dangerous tasks, to scout ahead, or they will simply take the form of vehicles. Anyway, I think you can clearly see that robotics and planetary exploration go hand in hand. Now let's take a look at the types of robotic spacecrafts. NASA unofficially classified 8 types of such: flyby spacecraft, orbiter, atmospheric spacecraft, lander, penetrator spacecraft, rover, observatory spacecraft, and communications and navigation spacecraft. I will not be going over all of those in this video as it will take too long, but if you want to know a little bit more about some of them, you can check out the link in the description. In this video, I will be talking about orbiters, landers, and I will be mostly focusing on rovers. First, orbiter spacecrafts. They are spacecrafts designed to travel to a distant planet and to enter its orbit. For that purpose, it must have a substantial propulsive capability, which basically means that it needs to be able to decelerate, to slow down at the right time so that it can actually enter the desired orbit instead of just flying by, which is essentially what flyby spacecraft do. Some other challenges that engineers and scientists need to consider while designing orbiters is that solar occultations will occur, which in simpler terms means the spacecraft will sometimes be in the shadow of the planet it's orbiting, which will obviously result in the spacecraft not receiving any sunlight, which in turn means solar panels will not be able to produce electricity, and the temperatures will drastically variate as the orbiter enters and exits the shadow. I couldn't find concrete examples, but from what I gathered, the temperature change would be at around 200 degrees Celsius, if not higher. It would, for example, drop from 100 degrees Celsius to minus 100 degrees Celsius and vice versa. So what can orbiters actually do in terms of exploring planets? While that obviously depends on the instruments installed and limitations of what's possible to measure from the distance of an orbit, the main gain, as simple as it sounds, would have to be the images of the planet it's orbiting. These images can be used to map areas of the planet, which in and of itself already provides some information about the planet, but furthermore, this enables scientists to better choose places of scientific interest, where landers and rovers can land, to measure the things that can't be measured from the orbit. Next, lander spacecrafts. Lander spacecraft are designed to reach the surface of a planet and survive long enough to telemeter data back to Earth. This involves some of the same challenges that the orbiter faces. The lander has to be able to operate in the temperature of its surroundings and to survive other possible hazards that particular landing spot presents. Not to forget, the lander has to actually land in a way that all of its subsystems and scientific instruments survive so that it can accomplish its mission. The tasks of a lander usually at least involve an analysis of the chemical composition of soil or rocks and imagery of its surroundings. And the last type of spacecraft I want to talk about is rovers. Rovers come in various forms and shapes, as pretty much any robotic spacecraft that is actually used on the surface of a planet that can move around is referred to as a rover. Rovers can be standalone spacecrafts that can do many things apart from moving around, like acquiring and analyzing samples, generating power, communicating with Earth, etc. They can also serve simply as extensions of a lander that can pretty much only acquire samples in order to increase a lander's reach. Or they can even be prototypes sent to test a single subsystem like mobility or communication. As such, it is difficult to classify rovers. Every rover is unique because it is tailored to the specific needs that arise from the rover's objective and the conditions it will be subjected to. Nevertheless, a classification is pretty useful, especially when learning about something on a surface level. So let's take a look at a simple division of rovers into four types that I personally think makes the most sense. Firstly, teleoperated vehicles, rovers remotely controlled from Earth, like the lunokhod. Secondly, robotic autonomous vehicles, rovers that operate autonomously to a certain degree, like Perseverance. Thirdly, human-operated vehicles unpressurized, rovers directly controlled by astronauts in spacesuits, like the Apollo Lunar Rover vehicle. And lastly, human-operated vehicles pressurized, which don't require astronauts to wear spacesuits and can almost be thought of as mobile bases, like Athlete. Despite having classified the rovers just now, I will actually focus on a single rover type. The reason being, well, obviously time constraints, otherwise the video would be too long, but also because for one, there haven't been missions involving human astronauts for a long time. And even if those return, they will still be very rare because, as I already mentioned, those are very dangerous and very expensive. They would require budgets that probably not even the United States would approve of very often, which means both human operated types get crossed out. Teleoperated rovers get crossed out for the reason that they can only be used on the moon. Rovers of that type are controlled from Earth, essentially like you would control an RC car with a camera. And as you might have figured out, this gets more and more difficult as the distance to the rover increases, because the communication delay increases proportionally. While controlling a rover this way is manageable on the Moon, where the delay duration is under 3 seconds, it is essentially impossible on any other body in the solar system, because the distance increases dramatically, and with them the delay that will take at least several minutes on any other planet in the solar system. And so, by process of elimination, we are left with autonomous rovers. In the following, I will mostly be talking about standalone autonomous rovers, meaning a standalone robotic spacecraft that doesn't require human presence on the planet it's exploring. A rover like that, to simplify, is essentially a lander on wheels. It has much of the same tasks as a lander and can perform them mostly as well. But there are obviously some trade-offs with the rover being able to move around. The mass and power necessary for enabling the rover to move can be used on scientific instruments on the lander. But as scientific instruments get better, smaller, and less power hungry, this becomes less of a problem. And the upside of being able to move around more than makes up for it. Unlike the lander, which is confined to the area it landed in, the rover can move around and visit multiple sites of scientific interest. Not to mention that landing spacecraft in a precise location isn't really possible, only to a certain degree. Meaning that if the lander misses the location of scientific interest, then that's it. There's nothing it can do. A rover, however, could just drive to that location, provided it's possible to reach it. So, as I already mentioned, you can think of rovers as mobile landers. But that is not entirely fair to say, because it makes it sound like rovers are strictly better. This is not the case. They are just better suited for different scenarios. The lander is better for global measurements that don't require moving around, as they can carry more instruments, while a rover is perfectly suited for regional measurements, which are different from site to site and require moving to those sites. Now that we have covered some of the basics about rovers, let's dig a little bit deeper by taking a closer look at Perseverance, NASA's latest Mars rover. Let's start by clearing up the autonomous part. As you might have guessed from autonomous being in quotation marks, autonomous rovers aren't all that independent. They are very much so controlled by rover operators, just like teleoperated rovers. The only difference really is that they aren't driven in real time with the help of a joystick. Rather, operators tell the rover where it should drive to, and the rover does its best to get to the destination on its own. To be able to do so, Perseverance has two navigation cameras mounted on a mast at the height of 2 meters for a better view. These two cameras essentially function as human eyes that allow the rover to see in 3D, which enables Perseverance to create a 3D map of the terrain with which it can then plan a safe route to the destination and execute it. As you probably noticed, Perseverance has quite a few more cameras apart of the two nav cams, of which hazard avoidance cameras provide additional help with the autonomous traversal of Martian terrain. They detect hazards like large rocks, trenches, and sand dunes to the front and back of the rover, which allows the rover to adjust its route accordingly so that it doesn't get stuck somewhere along the way to its destination. Another important camera is the Lander Vision System camera, which is responsible for landing the rover safely. During descent, this wide-angle camera takes pictures of the rapidly approaching surface, which a computer on Perseverance quickly analyzes and compares to an onboard map to determine the rover's position relative to the ground. This helped Perseverance during the landing in 2021 to autonomously pick the safest touchdown site within its landing area. In the infographic, you may have noticed that Perseverance actually has a lot more than one landing camera, but those are actually completely different cameras unrelated to the LVS camera. Unlike the LVS camera, those weren't actually necessary. They were an optional add-on that the team behind Perseverance added because they could. They did provide a cool short clip of the landing though, which NASA sadly haven't made publicly available. But you can check it out on YouTube. The link for the video is in the description below. The rest of the cameras that we haven't talked about yet are parts of scientific instruments, and I will talk about them later when we get to scientific instruments, but for now let's get back to the topic of mobility. Like previous NASA rovers, Perseverance uses a rocker bogie suspension system. The suspension system enables the rover to drive over obstacles, such as rocks, or through depressions as large as the rover's wheels, while maintaining contact with the ground with all 6 of its wheels. All 6 wheels come with their own motor. The 2 front and rear wheels also have individual steering motors to be able to turn in place a full 360 degrees. Perseverance's top speed is the same as its predecessors, 152 meters per hour. Despite that, Perseverance actually gets to places a lot faster. A significant improvement over Curiosity is the so-called thinking while driving capability, which allows Perseverance to process and analyze images while in motion, unlike its predecessor that constantly had to stop moving. This improved Perseverance's average driving rate from Curiosity's 17 meters per hour to 110 meters per hour, while having the same top speed. Another rather significant improvement over its predecessor are the rover's wheels. The wheels are narrower with a bigger diameter and thicker aluminum, which made them more robust, increased the size of obstacles the rover can drive over, and in combination with the new pattern, increased the rover's traction in soft sand and hard rocks. Perseverance carries 7 primary science instruments for acquiring information about Martian geology, atmosphere, environmental conditions, and potential biosignatures. Mastcam-Z is the name of the mast-mounted camera system that is equipped with a zoom function on the Perseverance rover. Mastcam-Z has cameras that can zoom in, focus, and take 3D pictures and video at high speed to allow detailed examination of distant objects. Its main job is to take high-definition video, panoramic color, and 3D images of the Martian surface and features in the atmosphere with a zoom lens to magnify distant targets. The SuperCam examines rocks and soils with a camera, laser, and spectrometers to see chemical materials that could be related to past life on Mars. It can identify the chemical and mineral makeup of areas on Mars as small as a pencil point from a distance of more than 7 meters. Its main job is to identify the chemicals in rocks and soils, including the makeup of their atoms and molecules. Mounted on the rover's robotic arm, Sherlock uses cameras, spectrometers, and a laser to search for organics and minerals that have been altered by watery environments and may be signs of past microbial life. In addition to its black and white context camera, Sherlock is assisted by Watson, a color camera for taking close-up images of rock grains and surface textures. Its main job is fine-scale detection of minerals, organic molecules, and potential biosignatures. The Planetary Instrument for X-ray Lithochemistry, also called PIXL, uses an X-ray spectrometer to identify chemical elements at a tiny scale. PIXL also has a camera that takes super close-up pictures of rock and soil textures. It can see features as small as a grain of salt. Together, this information helps scientists look for signs of past microbial life on Mars. Its main job is to measure the chemical makeup of rocks at a very fine scale. The Mars Environmental Dynamics Analyzer, also known as MEDA, makes weather measurements including wind speed and direction, temperature and humidity, and also measures the amount and size of dust particles in the Martian atmosphere. Its main job is to measure weather and monitor dust with sensors from the surface of Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, is helping NASA prepare for human exploration of Mars. MOXIE tested a way for future explorers to produce oxygen for fuel and breathing from the Martian atmosphere. Its main job is to produce oxygen from the Martian carbon dioxide atmosphere. Radar Imager for Mars's Subsurface Experiment, or RIMFAX, is a ground-penetrating radar that can image different ground densities, structural layers, buried rocks, meteorites, and detect underground water ice and salty brine at 10 meters depth. Its main job is to see geologic features under the surface. To power the motors and scientific instruments, among other things, the rover carries a radioisotope power system. The power source, called a multi-mission radioisotope thermoelectric generator, converts heat from the natural radioactive decay of plutonium into electricity to charge the rover's 2 primary batteries and keep the rover's tools and systems at their correct operating temperatures. This has a few advantages over the more common solar panels. The MMRTG provides a steady flow of electricity that doesn't depend on direct sunlight, which can be quite a problem on the dusty Moon and Mars, as dust tends to settle on the solar panels over time. This also means that Perseverance can operate at night. You might think that Perseverance would be very limited at night, with the cameras not being able to capture anything without sunlight, and you would be right partially, but there are actually quite a few things that Perseverance can still do. For one thing, MEDA continues monitoring the weather overnight as it doesn't care for the presence or absence of sunlight. But 2 instruments even take advantage of the night. MOXIE generally schedules its oxygen generation runs at night. This is largely because air temperatures are much lower then, which means the air is densest at night, which increases the amount of oxygen MOXIE can generate from Mars's carbon dioxide atmosphere. Sherlock also takes advantage of the night. This is because operating at night provides the least instrument noise, because the rover is a lot less active, and thus the most sensitive detections. You might think that with those advantages the MMRTG would have the disadvantage of not being able to supply the rover with power for a long time, But actually, the MMRTG's operational lifetime is 14 years. Admittedly, the power output gets lower and lower the more plutonium decays, but it still will be pretty high for the first few years, and it is very unlikely that the MMRTG will be the reason Perseverance stops operating. Next up, I want to talk a bit about planetary environments, specifically that of the Moon and Mars. Planetary environments are one of the biggest, if not the biggest factor when it comes to designing robotic spacecraft, especially rovers, because rovers actually need to traverse those environments, and because of the long communication delays, they need to do so autonomously everywhere except on the Moon. First, let's talk about the Moon. The Moon's surface gravity is about 6 times lower than that of Earth, and its temperature ranges from minus 150 degrees Celsius to 106 degrees Celsius at the equator, and gets as low as minus 230 degrees at the poles. It has no atmosphere. Due to constant meteorite bombardment over the eons, the lunar surface is heavily scarred by impact basins and craters. It is also completely covered in dust and rocky debris. The Moon is expected to have water in form of ice at its poles and permanently shadowed craters. The water would have been brought there by comet impact and stayed there because of the cold temperatures acting as cold traps. Confirmation of such water ice deposits is one of the major rationales for rover missions on the Moon, as those could serve as a water supply for future Moon bases. Mars's surface gravity is about 2.5 times lower than that of Earth, and its temperature ranges from minus 120 degrees Celsius to 20 degrees Celsius. Its atmosphere is primarily composed of CO2, about 95%, nitrogen, about 3%, and argon, 2%. It is also a lot less dense, almost non-existent when compared to Earth. The terrain on Mars is very varied when compared to the Moon, and I won't cover all of it, but here are some of its main features. As you can see on the map, the northern hemisphere of Mars is predominantly flat, while the southern hemisphere is mostly mountainous. Mars has 28 large volcanoes, none of which are active anymore, with Olympus Mons being the tallest mountain in the solar system with a height of 22 kilometers. One of the most exciting features of Martian terrain are the water-cut channels and flood basins etched across the surface, which suggest that Mars used to have liquid water and temperatures much closer to Earth. There is also evidence of water underneath the surface, where scientists hope to find life frozen in ice. Lastly, I wanted to at least mention the difficulty of realizing a space mission project. Space projects are absolutely huge. They involve huge teams, thousands of people, experts in all kinds of fields that need to work together to be on the same page and clearly understand the tasks at hand. They involve huge budgets of billions of dollars, which are numbers humans can't even imagine, yet need to be managed. And they involve tons of testing, especially if humans are involved in the mission, so that those human lives and the huge budgets aren't wasted. It is therefore really impressive how many successful missions there have already been up until now, including but not limited to the first crewed lunar landing and the several Mars rover missions. My hope is that this success continues and we will see a lunar or even a Mars base during our lifetimes.